Subject is there such a thing as the fourth dimension? Well, that was the Twilight Zone. Is this the same thing, four-dimensional?
Isn't
I
it?
mean, can you even imagine the fourth dimension?
Yeah, true. You can imagine the Twilight Zone. You
Well,
can't
it
imagine.
depends on how many beers you had. You know, what I mean,
No, I mean the Twilight Zone. You can imagine. They show it to you. It's a video.
okay, so
Fourth
we're
dimension? No.
no. Well, we're gonna start this segment with a fellow who uh, asked a question or made a comment. Okay, so we'll go with this comment first. Here it is. First fellow says, check 3D toilet paper sheet. Remove one dimension. Okay.
What?
If its thickness, it does not turn into 2D or a 1D. It turns into 0D. Okay. So you got 0D and 3D in the real world. So he's saying, look, you take toilet paper, right? It's 3D, right? You remove one of the dimensions, whichever one you want. And he says remove thickness, for example. Okay. He says you don't end up with 2D. The other two dimensions, you end up with 0D because there's nothing there anymore, just by removing one dimension. It's no kid.
What?
So 3D minus 1D is not 2D. 3D minus 1D is 0D, he says. Now, it took him a long time. I think he deserves a Nobel Prize. Okay, that's what I think. Okay? 3D minus 1D, that's new math.
You lost me.
3D minus 1D is equal to 0D, not to 2D. Okay? Same fellow, he says the following. He kind of laughs a little bit. He says, number of numbers, referring to the definition of dimension, okay? And he grins, okay? Yeah, if you look up the word dimension, okay? At least Wikipedia, you can look up anywhere, really. The minimum number of coordinates. That's the definition.
For what?
For dimension.
No, but the minimum number of coordinates for?
No, just the minimum number of coordinates, blah, blah, blah.
Minimum number of coordinates.
It doesn't matter what comes after that coordinate
That's
words.
the important part, isn't it?
No, this is the important part because they're defining what it is. It says number of coordinates. So what is a coordinate? It's a number. So we have the number of numbers, so he's laughing at himself. He doesn't realize that those are the definitions that the mathematicians work with.
Well, yeah.
In mathematics, a dimension is a number line.
Yeah.
Of numbers. So it is the number of numbers. That's what a coordinate, what a dimension is.
Does a line give it a direction already?
No, that's the point. The point is, I discussed that last week.
10 is after 8.
Yeah, but it's not.
Going in that direction.
But it's not. See, this is the point. That's not a direction. Numbers have no direction. I can put a number.
No, but a number line.
Yeah, but that's why they put it on the number line to give you the sense of direction when numbers have no direction. It makes no sense to put numbers in a given direction.
Okay, yeah.
That's the issue.
Because you can just as well flip them.
Yeah, or you can put them like I did the other day. I put them in different orders.
Yeah.
Like a 3 over here, a 4 over here. Are you going to hold it against me? I mean, there's no direction to numbers. And the point here is that the dimensions of math are not the same as the dimensions of physics, which are length, width, and height. So when they talk about dimensions, they're not talking about length, width, and height. At least not always. This is more or less like the dichotomy between weight and mass. Mass is sometimes weight and sometimes it ain't. Sometimes it's quantity of matter and sometimes it's how it presses up against the scale.
Yeah.
And when they want to use one notion, they use that one. When they use the other one, they use the other one. Nobody notices the difference because they always use the word mass. And this is something similar. Here they say, look, a dimension. And you say, well, are you talking about length, width, or height? No, I'm talking about all those numbers on the line. So you're not talking about dimensions of physics, but they use it in both senses. They say, well, it's this and it's also this. So they cover all the bases and they think they're doing physics, mathematical physics, because they're putting numbers underneath length or width or height.
I mean, sometimes they also say temperature is a number, is a dimension.
Yeah, and they have all these dimensions.
Once you say temperature is a dimension, then we got a problem because I mean, it's the same problem as time being a dimension, where it's like,
right.
People say we live in a 4D universe, but it's like, well, are you counting temperature? Then it'd be 5D. Are you counting the imaginary number line they came up with?
And that's exactly how they do it. They say, look, it's a dimension of laughing.
Yeah, because
what is that? What do you mean the dimension?
Forget 3 and 4 or 5 dimensions. There's as many as you can come up with.
And here it is.
And then the word just becomes meaningless at that point.
And here it is, okay? We started with the universal movie, and we're saying first that we're going to put number, line, and vector in the dynamic region, and dimension and coordinate in the static region. What is static? What is the universal movie? Well, a single frame only represents static concepts. And if you need at least 2 frames, as all those at the bottom, or more, you're gonna have dynamic concepts. Why? Because as you can see, the word number right there at the bottom is the verb to count. That's what it means. That's what the word number stands for. Number is the verb to count. Numeral is the symbol you use to represent counting. Okay, and number line and vector are both dynamic concepts. Vector is a dynamic concept because it's displacement. Okay, vector is what? Magnitude and direction. Direction of what? What do you mean numbers go in a given direction? Magnitudes go in a different direction? No, what it is that they say, look, here's A, we put an arrow to B, and something moved from A to B. But what they want to do is put some numbers there so they can say at what speed or what rate or whatever A went to B, or how much distance it covered or whatever. So a vector represents motion, always. That's why they would say magnitude and direction. But see, the word direction doesn't belong in math. You can't add directions. You can't subtract direction, multiplying. Direction is a word that belongs in physics exclusively, not in math at all. Okay, and this is where the problem is. They say magnitude and direction, the vector belongs to math. No, vector is one thing which it belongs to physics, and what belongs in math is the number line, which has nothing at all to do with direction. Number lines don't have directions, except in math.
We have our first question. How many dimensions does the flat Earth have?
Good question. It's the same question we addressed some time back. Yeah, it's not that.
It's like when I asked him
how flat is flat. And so if it's completely flat, it's like this guy says. You subtracted one dimension, you ended up with 0 dimensions. Okay, that's. But how flat is flat, and they always show it as a pancake, not as a flat. So it's not a flat Earth; it's a pancake Earth.
It's okay? The 2-inch,
and it's resting on turtles.
Yeah, turtles are flat.
All the way down.
How flat is flat?
Okay, so here's the recap for that. Okay, we have numbers, number lines, and vectors. They are dynamic concepts, whereas dimensions and coordinates are static concepts. In math, dimension, coordinates equal number lines. Okay, that's what they mean when they say coordinate or dimension. They're talking about number lines. Number line lacks direction. Number line has no reason to have any direction whatsoever. You don't put numbers in a given order except, to organize it for someone. But to actually think that numbers have direction is what's irrational.
Well, I think the irrational part is already the term number line.
Yeah,
line.
Line. The word line should not be in there. Okay? In fact, the word line does not belong in math either, because line and point, assuming it's a dot, right? They belong to physics. Those are objects.
Well, it depends on what line we're talking about.
Well, but
if we're using the
what I'm saying
conceptual one, then I guess you could put a floating number line there.
Like but I'm saying line is you cannot add or subtract lines.
Yeah, that's true.
It makes no sense.
Well, it doesn't belong. It would mean something else. It'd be like pickup sticks, lines.
But see, this is words that represent objects do not belong in math at all. You can't add or subtract tables. Yeah. Table minus table. You can add. You can subtract 1 minus 1, but not table minus table. You cannot subtract objects or tree from a table or whatever. Wood. Okay, and so number line lacks direction. Okay, therefore, infinite. Number line is infinite. Yeah, you can count forever. That's what infinite means, really, in math. Number lines. You can put, like you were saying a minute ago, that you have all these number lines, and if a number line is, temperature or time, you can put 1,000,000 of them. You can have the dimension of intelligence or whatever. Whatever you want. In math, 4D is equal to number lines. That's what they say when they say something is 4-dimensional. They're saying it's 4 number lined. Okay, that's what they mean. So when you see the tesseract there, tesseract is not 4-dimensional. They're saying it's 4 number lined. Okay, that's what it's all about.
But what about temperature?
Well, the same thing. It's number lined.
But it's missing there. That's right. Well, there's more dimensions then.
Well, yeah, I could add 1,000,000.
What about color dimension?
Well, no, the reason
size dimension. What about
no, the reason I put only that there, that number line, right? Because the tesseract is allegedly an object that has length, width, and height that is growing, that is expanding. Yeah. That's what a tesseract is supposed to be. So what is it expanding through? The dimension of time, they say.
That's you can see. It sounds so complicated.
Yeah, see, so it's all, what they're talking about is number lines. They're saying, we're going to use these numbers in our calculations, and we're going to call that result the tesseract. And they sneak it in there saying it's got length, width, and height. It's a cube, right? And you say, okay, I understand that. It's a cube. But what they're really representing is each one of those, length, width, and height, they're replacing them with number lines that have direction, and then they have this thing that has direction already, and now they're going to expand this moving object, this cube, right? They're going to expand it through time, which is that corner number line, right? And that's how you build the tesseract. So this is a moving object. This is not an object. This is an object that is expanding and it's moving through time. I guess, I don't know. This is how they handle it in math. Okay, but it has nothing to do with physics. This is not a physical object. Okay. And again, you can see the math number lines have nothing to do with the dimensions of physics. They also have nothing to do with the coordinates or vectors of physics. Okay. So what do we have? We have length, width, and height are the dimensions, physics. Coordinates are a way of locating an object with respect to other three reference points, which are at 90 degrees to each other, perpendicular to each other, orthogonal. And so what you have is altitude, latitude, and what's the other one? Longitude, latitude, and altitude. Yeah. And then vectors are depth, breadth, and elevation, because you're having motion. Depth, going deep, right? Breadth, sideways motion, and elevation, upwards motion. Okay, so those are the vectors that belong exclusively to physics. In math, none of those have any relevance. What they look at in math are number lines, and that's where people get confused, because are we talking about dimensions or are we talking about number lines? That's what you got to keep in mind. And here we have some questions for you, okay, for you to ponder today. Okay, we have these questions. Is there such a thing as the 4D, four dimension? Is there any object that is four-dimensional? Can you imagine any object that is 4D? If so, please draw it, and we'd like to see it.
No, you can't draw it. You can only imagine it. Well, I have it in my head, but I can't show you. Cheating. That's how I do that.
Yeah, put your head, give us a piece of your brain, your mind. Okay, is there an entity that is 10-dimensional, as string theory alleges? Okay,
10-dimensional. I can come up with way more than that.
Depends on how many beers you drink.
No, whiskeys. Off the top of my head, I can already come up with more.
And there you see my 16-dimensional universe. Okay, is that possible? Is that what you're staring at there? Is that a 16-dimensional universe? Or is it just a bunch of lines on a flat surface?
You're missing temperature, color.
Well, you can put anything you want in those. Like you say, you call it anything you want.
It's ridiculous.
Yeah, but here it is. Here we have the people in mathematical physics. They're going to put you straight. They're going to tell you exactly how they visualize dimensions. Okay, this is what this is about. Okay, can you visualize? Can you see? Are there such things as 4D and upwards? And here we have our first witness. This is what he's going to tell us. This is Mr. Stephen Hawking. He says, it is often helpful to think of the four coordinates. Look at his language, okay? Four coordinates of an event as specifying its position in a four-dimensional space. Coordinates in dimensional? He's mixing coordinates with his dimensions there. Called space-time. It is impossible to imagine a four-dimensional space.
It's easy.
Okay? No, but I mean, this is the guru, right? I mean, if he's telling you how it is, you got to accept it, on the basis of authority. So he's saying you cannot imagine the 4D. Okay, that's our first witness. Okay, now we have another one. Here's good old Einie, okay, and this comes out of the Wikipedia. And what does he say? He went on to the other side. Give me a second here. Get it back in there. Okay, so it says, in everyday life, there are three familiar dimensions, 3D of space, weight, height, width, and length. Einstein's general theory of relativity treats time as a dimension on par with the three spatial dimensions.
I like that. Spatial dimensions.
Yeah, spatial.
Also known as dimensions.
The spatial dimensions. In general relativity, space and time are not modeled as separate entities, but are instead unified to a four-dimensional. So they're treating time as a dimension, right? So, yeah, you're right. Why do they say 3D when it's 4D, right? They're all the same. In fact, Hawking tells us there's no difference between the time dimension and the space dimension.
But then why would he make a difference for the temperature dimension?
Yeah, ask him.
I'd love to ask him.
Yeah, but he's up there in heaven or hell. Yeah.
It's just really that they don't need it. That's all they say.
It says, in this framework, the phenomenon of gravity is viewed as a consequence of the geometry of space-time. But then on the right-hand side there, you see all the string theorists, okay? And they say something different. They say, in spite of the fact that the universe is well described by 4D space-time, there exist scenarios in which there could actually be more than 4D, than the four dimensions of space-time, which have nonetheless managed to escape detection. So we cannot detect these dimensions, okay? That's what these people say. These are the string theorists, okay? And they're trying to unify quantum with relativity. That's what their business is. That's what their job is. Here they are again. So string theories require extra dimensions of space-time. So they can't just live with general relativity at its four lousy dimensions. They need to have a lot more, okay?
We're just talking about locating something, right?
Well, let's find out. Let's find out what these people tell us. It says, for their mathematical consistency, in bosonic string theory, space-time is 26-dimensional, while in superstring theory, it is 10-dimensional, and in M theory, it is 11-dimensional.
Did you ever look up what these dimensions are exactly?
Well, I wish they would name them so we knew what they are.
They don't name them?
No, of course not. They just say, because they're talking about number lines. They're not dealing with dimensions at all, but they call them dimensions. And that's what confuses people. They're talking about number lines. In order to describe real physical phenomena using string theory, one must therefore imagine scenarios in which these extra dimensions would not be observed in experiments.
What?
So you can't detect them through in experiments, but they're out there. Kind of fishy. It's like saying, we know they're there, we're the mathematicians, you got to believe us, but we can't find them even through experiments.
Well, I mean, for fairness, we say the same thing with the ropes, right?
Yeah, but see, this is the issue. We're not asking people to believe. We're saying, look, we're going to make an assumption that there are ropes out there, right? This is not what these people are saying. They're saying, we proved it. We know. We certified.
That's what they cross over.
And why can't we see them? Well, it's called compactification. That's why we can't see them or detect them with experiments, is one way of modifying the number of dimensions in a physical theory. In compactification, some of the extra dimensions are assumed to close up on themselves to form circles. We have curved dimensions here, right? If the hose, listen to this is the example they give. If the hose is viewed from a sufficient distance, it appears to have only one dimension, its length. If you can see it from anywhere, it's got at least two dimensions, but they say it's got only one dimension, and that's length. Okay, we'll accept that for a moment. However, as one approaches the hose, one discovers that it contains a second dimension, its circumference. So circumference is now a 2D dimension, a two-dimensional thing, right? Thus, an ant crawling on the surface of the hose would move in 2 dimensions. So they're talking about moving in 2 dimensions. I thought motion had to do with vectors, but here they're saying it's dimensions. And this is the punchline here, okay? Here's these fine gentlemen. They say, in physics, string theory is a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional objects called strings. So the string is one-dimensional. And the question is, what dimension does it have? Length, width, or height?
Numbers.
Well, yeah, numbers. That's what they're talking about, okay? They're not talking about dimensions at all. Okay, and they call them strings. Okay, and string theory describes how these strings propagate through space. So we have one-dimensional strings, which no one can imagine. We cannot imagine a 0 or a 1-dimensional or a 4-dimensional string.
You're saying they're not skinny. They are literally one dimension.
Yeah, because they're talking about number lines. They're not talking about dimensions. So they say, look, we have all these numbers.
We don't need length with the height. We don't even need to imagine it. Right. We just care about the number line, right? Forget the... But they're giving a dimension to the number line.
Yeah, but listen.
That's what I get. Hold on. Can I just really quick interject?
Yeah.
This string that they're talking about has one dimension, right? Or they say it like that. But aren't they just saying that they're only using one number line because that's all they need?
Exactly.
So why call it a string? Why call it a dimension? Why give it all these things?
Because the word string immediately takes it into physics.
Yeah, that's the bottom.
So it's misleading to say string because people imagine, this is a string. People say, okay, I understand what a string is. Here it is in black, right? I know what a string is. It looks something like that, right? So people say, okay, I know what string is. What you're staring at is not one-dimensional because otherwise you couldn't see it, okay? It's at least two-dimensional, right? At least from your point of view, because you have length and, you have width and height there from your vantage point, okay? You have width, which is sideways, right? And height, which is the thickness of the string. So you have 2 dimensions. They call this one-dimensional. That's the problem.
Well, they don't call that one-dimensional.
Well, they call it because
what they do is it's the other way around. They take a number line and call that a string, which is what people think is.
But they tell you that's one-dimensional.
Well, it is because it's a one. But what they're saying is we have one number line.
Yeah.
The one-dimensional one number line, and we're gonna call that a string. No, don't call it a string. String makes it sound too.
Don't call it a dimension.
Yeah, don't call it a dimension either.
I mean, this is the issue. They call it a dimension when it's not even 1D.
And physical and dimension makes it sound real.
But look at the example they give you: a hose. And they say you look at the hose from far away, it's 1D. No, it's 2D from anywhere in the world that you can see it. If you can see it from the other side of the universe, it's still 2D, at least, if not 3D. But for sure 2D. It's not 1D. But they say what you're staring at is what is 1D, and that's where they make the error. And they say, if it's 1D, it's only length, and if it's length, it's a string. So that's how they make the transition.
Real quick, is there anything in that exists that isn't exactly three-dimensional?
No.
Okay.
3D, everything is.
Everything that exists is exactly three-dimensional.
Exactly. 2D does not exist. 2D, you can think of it this way: a square is the face of a cube. So you're staring at the square. Let's say you just stare and you can't see the rest of the cube behind it. We say that's a square. That's a 2D object.
But we only
that's what you're seeing.
But essentially, what we do is we're saying, well, we don't need the third dimension, so we're just going to do without it. Because they do that in programming also, where they just basically throw away the z-axis because they're like, okay, for this object we don't need it, so it's two-dimensional only because we don't need the third one. And these guys took it a step further. They're like, this is one-dimensional because we don't need the other two.
Yeah,
we don't need more, so let's just call it one-dimensional. But there's no such thing as a one-dimensional or a two-dimensional. Right, it's just how many dimensions do we need for that object?
Yeah, but what I'm worried about is what these people are saying, because they're saying that this is one dimension. Because you're seeing it from far away and you say, well, that's just one dimension. No, this is two dimension. If you can see it, it's at least 2D. Yeah. And they think that a line, in geometry, they say a line is 1D. No, a line is 2D. Yeah. And a point is 2D.
A number line is one-dimensional.
Even the
length,
because the line is the dimension, not the numbers. The numbers are concepts.
You know something that is one-dimensional? Length.
No, the minds of these people. That's what one.
Width is one-dimensional.
Yeah. Okay. So here we have these people are saying that the hose is 1D, and you can see it's at least 2D, but they call it the 1D hose. They have the little ant crawling around it, and they say the ant is going around in 2 dimensions. No, that's not dimension. Those are number lines that they're talking about. The ant only lives in 3D world. Okay, but these people call that 2 dimensions. And there you can see on the bottom left an example of compactification. At large distances, a 2-dimensional surface with one circular dimension looks one-dimensional. No, that's
looks
not
one-dimensional.
Now, is that one-dimensional? It looks like 2-dimensional still to me. It looks one-dimensional.
That's an oxymoron. Looks one-dimensional. What do you mean looks one-dimensional? If it's one-dimensional, I can't look it, can I?
But this is the issue. They point to a 2-dimensional object. You're staring at it. You drew it, on the board, and they say that's 1D.
I'm gonna say that to my skinny buddy next time. You look one-dimensional, bro. You gotta eat something. You look one-dimensional. Okay,
so this is what the strings look like.
What?
Do they look like one-dimensional things, whatever?
They look like what?
At least I would say
bubbles.
Well, no, because you're supposed to see them as just a 2-dimensional, one-dimensional thingy.
Is it okay? Is it 2 or 1? Come on.
Yeah. Well, they're saying that these wigglings are what creates it. So what you're looking at is the particles, and they say a particle is really a vibrating one-dimensional string. But I see that it's got 2 dimensions. Otherwise, I wouldn't see it, right? Yeah. If it's one-dimensional, we wouldn't see it at all, right? And so, they have it vibrating back and forth. And they say the different vibrations are different particles.
You don't understand. This is for dramatic effect, but
yeah.
They don't actually look like that.
Yeah, but see, they're trying to illustrate something which is unillustratable. It's unimaginable, let alone illustratable. You cannot imagine.
For the dummies like us, boss. We're a little slow. They got to show us the flashy lights.
Okay, let me tell you what the story is. In the old days, people believed that you die and your soul goes to heaven.
What?
Right?
What?
Your soul goes to heaven, right?
Okay, yeah, but this
comes out.
Tangent. Where are you going with this?
Okay, you'll see where I'm going. You'll see where I'm going with this. Okay, so here's.
Don't tell me the government lied about that too. I want to go to heaven.
Okay, so here are the people going to heaven. This is the way it used to be. Okay, it was normal stuff.
God closed the gates or what?
Yeah, people would die, all over the earth, and they would slowly, seep into heaven. And today we have something different, or something similar, really, almost exactly alike. And it's this fellow Brian Cox, and he says that all these gravitons that produce gravity, they go to some unseen dimensions. And this is what it looks like, I guess. Gravitons going into this 4-dimensional world. Okay, and this is what Mr. Cox says. He says, look, the reason gravitons disappear is that they vanish into a place beyond our reality, into some sort of extra dimension. There can be extra hidden, unseen dimensions. It sounds ridiculous, and it is impossible to picture. But theoretically, it is possible. That's what he said. Wow. This is a so-called physicist, okay? And it's also possible that gravitons, the particles of gravity, can spend most of their time in those extra dimensions. Okay, so gravitons
most of their time.
Yeah, so
like they're people.
Yeah, they spend all their time, going to this four-dimensional heaven.
What?
It used to be the souls that went there. Now it's the graviton.
Come on,
So
you wrote that.
these guys haven't invented anything new. They're just replacing souls with gravitons. So the reason we don't see the gravitons is they're over there in unseen, undetectable dimensions.
I got a question. Is the rope one-dimensional?
No, absolutely not. 3D. Everything that exists is 3D. Your rope exists, you could say, because it stands between two objects, and for that we have to define exactly what the word exist means and what an object is.
It's even 3D as far as imagining the structure.
Yeah, well, 3D. I mean, that's what a rope is. That's 3D, and we're not kidding anyway. We're not saying this is 1D or 2D. This is 3D. Okay, and we're saying the rope is 3D. Okay, the rope is 3D. It's just so thin, so tiny that we cannot see or detect it, and it's untouchable, unseeable. And you say, Bill, you're introducing ghosts and goblins. No, we're saying that
Ghosts
an object.
And goblins is saying 1D. That's ghosts and goblins.
We're saying that a rope is this. This is a rope, and it's 3D, and that's what we're saying it is. 3D, no problem there. Okay, hopefully. And you say, well, we can't touch it or see it. Then you're introducing, fantasy. No, because an object is not that which you can see or touch. An object is that which has shape, and hopefully this has shape. So we met the condition for an object. Now for existence, we need to have it location in the universe with respect to the rest of the matter in the universe, and a rope does have that. So yes, the rope exists under that definition. And that's just to produce the hypothesis. A hypothesis is something you take at face value in order to understand the theory founded upon it.
As far as the Cox guy, right?
Yeah. It kept you rolling, huh?
Well, yeah, because it's just amazing to me how physicists are still so full of...
Don't call them physicists. Well, please.
Whatever you want to call them. Mathematicians.
Yeah, that's better.
Even they who dedicate their lives to science, or at least try to, are so filled with, like, poetry, metaphor, a superstition. It's no wonder that there's still religion around.
Well, a lot of the people out there, they want real answers. They want to know why this pencil falls to the floor. That's all we need to answer. They haven't been able to answer the answer. They haven't been able to answer that in 10,000 years. That's weird. And how difficult can this be? Here we have...
I mean, it's difficult.
Oh, it is?
It is.
No, the only reason it's difficult, you cannot see the mediators. And that's why we're saying the mediators are the ropes.
It's easy to you because you already got the answer. If you know the joke, obviously it's easy. But until you know it, it's hard.
Yeah. Anyways, here's the rundown, the conclusions for today. We have it. Mathviz, mathemagics, has three branches: general relativity, quantum mechanics, and string theory. Relativists confess that they can't even imagine the 4D, let alone see it. Okay, so that's out of the way.
I can imagine a lot of 4Ds.
Okay, well, but they're talking about length, width, and height, and time, and they're thinking about the hypersphere or the hypercube, and they say you cannot imagine. Okay, great. So that rules the 4D out. But then we have quantum mechanics. It doesn't deal with dimensions at all, right? And then string theory proposes 10, 11, and 26 dimensions. You take your pick, okay? Whichever theory you subscribe to. String theorists admit that they can't see these dimensions, right? String dimensions are curled up and compacted, okay? So they're curled up into little curlicues, and that's why you can't see them. And mathematicians allege that quantum mechanic gravitons hide in unseen, undetectable dimensions.
And that's another way that they use the word dimension. In fact, that one's used far more often in fiction and movies and such. Dimension, what it really means in like just day to day, it doesn't really mean length, width, and height. What it means is an alternate reality.
Yeah,
that's how they use it. That's how they use the word there, where they say that graviton is in another dimension. They're not even talking about length, width, height, temperature, or time. They're just saying it's in a different reality. So that's extra confusing when they use the word dimension.
And there's something.
Why do they use the dimension in both terms when we're supposed to be doing science here? Like, pick one. They can't be both.
That's one issue. The other issue is that you notice that because they cannot answer any question, they cannot answer gravity specifically, they put all these dimensions beyond your grasp or beyond your understanding. They say, well, we don't understand it. It's out there. All the gravitons go to this heaven that we can't see, this 4D heaven. And so they put it beyond your reach. Yeah. So you say, oh, that's so awesome.
Oh, they know so much. They're so wise.
Yeah, because they put it beyond your reach. Your understanding, they put it beyond your imagination.
Thank Higgs for these guys, because, man, we're too dumb to understand this 26 dimension thing.